Using an ungrounded 240 volts three-phase delta system presents several dangers. Firstly, there are electrical shock hazards. Stray currents can flow through exposed metal parts in ungrounded systems, increasing the risk of electrical shocks. Capacitive coupling between ungrounded conductors and earth can create a path for current to flow, leading to shocks. Without a proper ground, lightning strikes can induce currents in the system, also posing a shock hazard. Secondly, equipment damage is a major concern. Open neutrals or imbalances can cause overvoltages that can damage rotors, transformers, and other equipment. Non-grounded systems are more susceptible to harmonic distortion, which can overheat equipment and shorten its lifespan. Stray currents and harmonic distortion can lead to premature corrosion of metal components, causing equipment failures. Thirdly, there are fire hazards. Non-grounded systems have a higher risk of arcing faults, which can ignite fires. Excessive current flow due to overvoltages or imbalances can overheat equipment, potentially starting fires. Other hazards include electromagnetic interference or EMI. Non-grounded systems can generate electromagnetic interference which can disrupt electronic devices and communication systems. Fluctuating voltages without a stable reference ground can cause problems for sensitive equipment. Furthermore, non-grounded systems do not meet electrical safety codes and can pose a hazard to workers and personnel. According to the 2008 National Electrical Code or NEC, proper grounding is crucial for safety, equipment protection, and compliance. Ignoring these recommendations can lead to serious consequences. It is essential to ensure that any electrical system, especially a 240 volts three-phase delta system, is properly grounded to mitigate these risks. The absence of grounding can create pathways for fault currents that would otherwise be safely directed to ground, tripping circuit breakers or blowing fuses. Without this protection, these fault currents can persist, leading to overheating, arcing, and potential fires. The increased risk of electrical shock is a primary concern in ungrounded systems. Since there is no direct path for fault currents to return to the source, exposed metal parts of equipment can become energized, creating a dangerous touch potential. This means that anyone coming into contact with the equipment could receive a severe electrical shock. Overvoltages in non-grounded systems can arise from various sources, including switching surges, lightning strikes, and unbalanced loading. These overvoltages can stress the insulation of electrical equipment, leading to premature failure. Motors, transformers, and electronic devices are particularly vulnerable to damage from overvoltages. Harmonic distortion is another significant issue in non-grounded systems. Harmonics are currents and voltages with frequencies that are multiples of the fundamental frequency of the power system. These harmonics can cause a variety of problems, including overheating of transformers and conductors, increased energy losses, and interference with electronic equipment. In non-grounded systems, harmonic currents can circulate more freely, exacerbating these problems. Corrosion is accelerated in non-grounded systems due to the presence of stray currents and harmonic distortion. These currents can cause electrochemical reactions that corrode metal components, leading to equipment failures and safety hazards. Arcing faults are a major fire hazard in non-grounded systems. An arcing fault occurs when current flows through an unintended path, creating a high-temperature arc. This arc can ignite nearby combustible materials, leading to a fire. Non-grounded systems are more prone to arcing faults because there is no low impedance path for the fault current to flow, which would quickly trip a circuit breaker. Electromagnetic interference, or EMI, is another concern associated with non-grounded systems. EMI can disrupt the operation of electronic devices and communication systems, leading to malfunctions and data loss. Voltage fluctuations in ungrounded systems can cause problems for sensitive equipment, such as computers and medical devices. These fluctuations can lead to erratic behavior, data corruption, and even equipment damage. In addition to the technical risks, non-grounded systems also pose safety concerns for workers and personnel. The lack of grounding makes it difficult to detect and clear faults, increasing the risk of electrical shock and other hazards. Non-grounded systems do not meet the requirements of most electrical safety codes, including the NEC. Compliance with these codes is essential to ensure the safety of electrical systems and to protect workers and the public. The NEC provides detailed requirements for grounding electrical systems, including the size and type of grounding conductors, the location of ground electrodes, and the bonding of metal parts. These requirements are designed to minimize the risk of electrical shock, fire, and equipment damage. For example, NEC Section 250.4 addresses general requirements for grounding and bonding. NEC Section 250.20 specifies which systems and circuits are required to be grounded. NEC Section 250.50 details the grounding electrode system. NEC Section 250.166 covers sizing the grounding electrode conductor for alternating current systems. Grounding ensures that in the event of a fault, a large current flows through the grounding conductor back to the source, tripping the overcurrent protection device like a circuit breaker. This rapidly de-energizes the circuit, preventing prolonged exposure to dangerous voltage levels and reducing the risk of electric shock. Proper grounding also stabilizes voltage, reducing voltage fluctuations that can damage sensitive electronic equipment. Grounding provides a reference point, limiting overvoltages that can occur due to lightning strikes or switching surges. Properly grounded systems reduce the risk of fire by quickly clearing ground faults before they can escalate into arcing faults. The low impedance path to ground allows high fault currents to flow, activating overcurrent protection devices promptly. Addressing harmonic distortion is another benefit of grounding. A well-grounded system provides a path for harmonic currents to flow back to the source, reducing their impact on other equipment and the overall power system. Grounding helps mitigate electromagnetic interference, or EMI, by providing a shield that reduces the radiation of electromagnetic energy. Grounding also reduces corrosion by minimizing stray currents that can cause electrochemical reactions. Ensuring compliance with electrical codes, like the NEC, is vital for the safe and reliable operation of electrical systems. Grounding is a fundamental requirement in most electrical codes, aiming to protect people and property. When evaluating an electrical system, it is essential to check the grounding system for proper installation and maintenance. Verify that all grounding conductors are properly sized and connected, ground electrodes are installed correctly, and all metal parts are bonded together. Regular inspections and testing can help identify and address any issues before they become major problems. In summary, while a non-grounded 240 volts three-phase delta system might seem like a simpler or cheaper option initially, the risks associated with it far outweigh any potential benefits. The dangers include electrical shock, equipment damage, fire hazards, electromagnetic interference, voltage fluctuations, and non-compliance with safety codes. Properly grounding the system is a crucial step in ensuring the safety and reliability of the electrical system and protecting people and property from harm. The NEC provides comprehensive guidelines for grounding electrical systems, and compliance with these guidelines is essential. It's important to consult with a qualified electrical engineer or electrician to ensure that the grounding system is properly designed and installed. The risks of not doing so can lead to serious consequences. Ensuring that your electrical systems are grounded and maintained will reduce the chance of hazards and protect workers and equipment. In the context of a 240 volts three-phase delta system, the grounding method significantly impacts safety and equipment protection. Grounding transforms the system from an unreferenced, potentially dangerous configuration into a safer, more predictable one. In a delta system, the absence of a neutral point means that the voltage to ground on each phase is not fixed. This can lead to voltage imbalances and higher than expected voltages on some phases relative to ground. When a ground fault occurs in an ungrounded delta system, it may not be immediately apparent. The system can continue to operate with one phase faulted to ground, but this condition puts increased stress on the insulation of the other phases and increases the risk of a second fault, which would result in a phase-to-phase fault and a much larger fault current. Grounding the delta system, typically through a corner grounded delta or a high resistance grounded delta, provides a reference point and limits the voltage to ground. In a corner-grounded delta system, one of the phase conductors is directly connected to ground. This makes the system behave similarly to a grounded Y system, with a fixed voltage to ground on each phase. However, that also means that a ground fault on the grounded phase will not be detected by overcurrent protection devices, as it is essentially a normal operating condition. In a high-resistance grounded delta system, a resistor is inserted between one of the phase conductors and ground. This limits the ground fault current to a relatively low level, typically a few amps. The low fault current reduces the risk of arc flash and equipment damage, while still allowing the ground fault to be detected and located. There are several methods to ground a 240 volts three-phase delta system, including corner grounding, midpoint grounding, and impedance grounding. Firstly, in corner grounding, one phase conductor is directly connected to ground. This is the simplest method but can result in high fault currents if a ground fault occurs in the grounded phase. Secondly, in midpoint grounding, the midpoint of one phase winding is connected to ground. This method is commonly used in delta systems that supply single-phase loads. Thirdly, in impedance grounding, a resistor or reactor is inserted between the neutral point and ground. This limits the fault current and reduces the risk of equipment damage. The choice of grounding method depends on the specific application and the desired level of protection.